where all the action is. And those of you who will be fortunate enough to be at the frontier, you will realize that you have behind you things that are known, and in front of you things that are completely unknown. And in the world, there are some people who move that frontier out. And these people are very difficult to capture within conventional disciplines. Is this person a physicist? Is this person a chemist? Is this person, is this person doing partial differential equations? There are definitions, and these definitions capture you and make you captive of the definition. So our idea here is to bring to you people who challenge this notion that they are captives of some definition of what they do. And it is, they are not many, they are rare, and therefore we prize them, we take great pride in them. And I think that it will be a great service to this institution, particularly for the younger people, when you get to actually see examples, real life examples of people who are pushing the frontier. And today we have amongst us a very, very dear friend whom I have known for many years. And Satish will tell you about him. And please tell your friends that these kinds of talks and colloquia will happen. And please make sure that even if the abstract looks formidable, don't be afraid, because these are unique people who will tell you something that you will go home more enriched than the way you came in. And with all of that, I just wanted to hand it over to Satish, who will introduce our speaker properly. Thank you for coming.
Not a problem.
How to introduce properly. I don't want to say something. Be short. Okay, so it is a great pleasure to introduce today's speaker, my friend of maybe 35, 40 years time. And he's one of the exceptional physicists of this country, known internationally for his astute kind of contributions and choice of research problems, and how deeply he follows the principles of science in whatever best manner it is possible. He has a brand of highly eminent students. So you can imagine, it is not simply one or two or a few or something like that. It is a full brand of about 20, 30 people, 40 people who are in the best academic positions everywhere. It is not industry or something like that, but academic positions of the highest order. And they have won several awards internationally as well. So you can imagine how he has trained young minds from the domains of IIC. And I have always said that I am the fan of his research, because it is not simply doing a publication, but if you read his publication, the depth it reflects of whatever issue he is trying to address, that tells you that it's a joy to read his publications in science. So it is a pleasure to introduce him. Just I'm reading a few things because there are so many things in his, all the pages of his career that I don't want to miss some of them important ones. I'm sure there are many more things, but I will just read a few things which are very important. So Professor Dipankar Das Sharma, his name I am reading because as Shobhoda said, DD, beyond DD, nobody knows. So maybe they don't know is Dipankar Das part of it. Is our DD, okay? Popularly known as DD, he is the structural chemist known for research in the field of solid state chemistry, spectroscopy, condensed matter physics, material science, and nanoscience. He is a former MLS Chair Professor of Physics and Chairman of Center for Advanced Materials and the GAST Professor of Uppsala University, Sweden. He has also been the J.N. Tata Chair Professor at Solid State and Structural Chemistry Unit of IISc, Bangalore. Also an honorary professor of JNCSR Bangalore and SN Bose National Center for Basic Sciences in Kolkata. He is also an eminent visiting fellow at IACS Kolkata. He is a recipient of several national and international honors, including the TWAS Prize in Physics, the UNESCO Biennial Javed Hussain Prize, the coveted Shanti Swarup Bhatnagar Prize, of course, of CSIR, honoris causa doctorate degree from Uppsala University, Sweden, the Knight of Order of the Star of Italy by the Republic of Italy, to name a few. He's an elected fellow of Asia Pacific Academy of Materials, 2008, fellow of American Physical Society, 2007, and the fellow of all the academies of science, eminent academies of sciences of India. So with this brief introduction, I would say it is brief because if you go to DD Sharma page on website, it just rolls on. Okay, so it is a pleasure, DD, to have you here. Thank you for accepting the.
Thank you, Satish, for the embarrassingly long introduction. There's a saying that we used to have in our childhood days that in a marriage, the groom shouldn't be dressed up too much so that the groom doesn't outshine the bride. Similarly, there's a theorem about seminar. The introduction of the speaker should never be longer than the seminar itself. You nearly violated that today. Thanks a lot, Shobhu. Thanks a lot, Satish, for making this possible. I mean, there are so many very important people in my life that are sitting here. Shobhu, Satish, Devashish, GP, Bhupen, Biplav is somewhere there. Shona I have known for a very long time. It's really wonderful feeling to be here. And I'm really grateful for making it possible. And TCG CREST, one that Shobhu made, is doing this very extraordinary and important experiment in education and research. And it must succeed because that is actually the true model of what education and research ought to be. And somehow we don't pursue that in more conventional institutions, including our own, where they are very tradition bound. So I'm really glad that you're breaking the frontiers or the shackles of the tradition and doing it in a different way. And I visited the RISE Center today, and I'm very impressed, and I congratulate everybody there. And I'm sure the other three verticals are as important as the one that I have seen at RISE. So I hope that I'll have occasion to come back and interact with all of you a lot more. What I'm going to talk about today is this slightly tongue-in-cheek title that I've chosen, 2D or not 2D, and I'll try to justify why this title. But basically, if I have to give you a subtitle of this particular talk, what I'm going to talk about is two-dimensional and three-dimensional, something that you don't have to worry about right now because there's a lot of cliche here, and I'll try to explain to you what those are so that you get a feel for what I'm talking about. So, of course, the three-dimensional is not 2D, and the two-dimensional refers to 2D, but it will go a little more beyond this rather simplistic explanation. Let me get started by telling, because I tend to forget to acknowledge the funding, which is, of course, extremely important, and I've been generously funded by DST, SERB, and more recently by CSIR, which sustains all of our research in recent times, at least with very generous support through this National Fellowship Program. What the plan of the talk is going to be that I'll first introduce this horrible name that you find here, hybrid halide perovskite. What is it and why you were very excited about it? And really the world is extremely excited about it. A very large fraction of condensed matter scientists and material scientists and energy scientists and nanoscientists, these very large segments have sort of converged onto investigating these materials, and there's a very good reason for that, because they also hold out tremendous possibilities of commercialization. And I'll try to give you a feel for what those excitements are all about. That's going to be really the 3D part of it, which I said is not 2D. But then if we are fine with such fantastic properties of 3D materials, why should anybody bother about low dimensional system, let's say 2-dimensional, 1-dimensional, or 0-dimensional system? And that's when I'll introduce to you the concept of the 2D counterpart of these materials. And basically, I'll show you that these offer the kind of design flexibility of material properties that is not available at this level. So there's some reason one has to look at these lower dimensional objects. And after introducing that idea, I'll take a specific case study to show what one can do with this designability that I have talked about here, how you can make use of it and arrive at some very interesting properties. And if time permits, very briefly, I'll touch on in the last case study, where I'll show that having discussed about this in terms of very strict dimensionalities of 3-dimension and 2-dimension, how the material properties sometimes defy the strict classification based on dimensionality, where it's difficult to figure out whether it's a 0D, 1D, or 2D object, because different kind of properties require you to appeal to our senses, that saying that this property, look, it comes from the 0D, but in the same material, some other property comes from 1D or 2-dimensionality. So it's a quasi-dimensional system, and I'll give that example rather briefly at the end. So let me get started with what I've promised, what these hybrid halide perovskites are. Well, a perovskite is a very simple object. It's a crystal structure that has afforded tremendous amount of excitement in condensed matter physics from time immemorial. I mean, they underline almost every kind of properties: magnetism, electricity, dielectric properties, superconductivity, colossal magnetoresistance, catalysis. You talk about it and you see examples, not only examples, fantastic examples realized in perovskite structure. What is a perovskite structure? It's very simple. Think of a cube, and you can see a cube here. And think of a chemical formula, let's say A, B, X, 3. A is some element, B is another element, and X is the third element. Take the B element and put it at the corner of the cubes. So that cube corners are now all occupied. And then the X element, which has 3 times the number of B element, take the edge center of the cube and put it at the edge center. So there are 12 of them, and there are 8 of them. These 8, each of them are shared by 8 cubes, and that's how it comes out to be 1. Similarly, if you count, each of them are shared between 4 cubes. So there are 12 of them divided by 4. That comes out to be 3. Now that gives you the basic structure. You can also think of it as, if you look at this B atom here, there are 6 X atoms around it, forming a BX6 octahedron, a very regular structure. But the interesting part of it is that this particular X atom is shared between this octahedron and the octahedron that we'll construct here. Likewise, this B atom is shared between the octahedron around this one and around that atom. Similarly, this one is shared between this and that one, which means that you can also think of this structure as BX6 octahedron, corner shared. These are the corners in all direction, in this direction, as well as in that direction. And that forms the magnetic, optical, and electronic properties and dielectric properties of these materials very often. Having said that, but this kind of a structure, you can see there will be a very big void at the center of the cube, and so it often is unstable. In order to stabilize, you put that A that I said, ABX3, A atom at the center to stabilize the structure. Very often we say that that only is needed for stabilizing the structure, and the main properties that we are interested in is derived from this BX6 octahedron corner sharing in all 3 dimensions. And we forget about the A atom. That's your perovskite structure. This new material that I'm talking about, first of all, the X would be a halide, and that's why it's called a halide perovskite structure. And instead of putting an element at the center, making it all inorganic, so lead at this corner, all examples I'm going to talk about up to the last but one example, it's going to be lead at the corner. And it's going to be one of the halide ions, which can be iodine, bromine, or chlorine at the edge center position. But instead of putting some kind of an inorganic element here, if you put an organic molecule, because it's a large void, and you can fit in an organic molecule to sit there, and that's why it's called a hybrid material. Hybrid refers to the fact that it's neither inorganic nor organic, but it's a hybrid of inorganic and organic material. And that particular can be this methyl ammonium group that is shown over here. Very often I'll refer to it as short form MA, and MAPBX3 is this perovskite structure. So that defines why we call it perovskite, this structure, why we call it halide, because this X is a halide ion, why you call it hybrid, because at the A site I can put one of the organic molecule. Two organic molecules that fit in there easily is a methyl ammonium and formamidinium. Most of the time, you don't have to worry about them at all because it sounds very crazy, methyl ammonium, formamidinium. It took me quite a while to pronounce it correctly because it's not is formamidinium. You don't know where the N is and where the M is. But the belief is that you don't have to worry about its properties because the properties are controlled by the PBX6 octahedron that I have already mentioned. And you can also make a solid solution of this MA and FA, and that is known to sort of stabilize the system better to get better properties. Why are you excited about it? Because this is really the new kid on the photovoltaic block. Let me try to explain what I mean by that. This particular compound is not recent. It's been known for a very long time. And the first person, Professor Miyasaka, who started working on this gentleman, and he's been working on it a long time back, nearly 20 years ago, trying to get a solar photovoltaic out of that. The reason he was interested in that, because he knew that the band gap of this material is in the order of 1.5, 1.6 electron volt. And that's nearly the ideal band gap of getting the maximum power by absorbing solar light. Because you know that, of course, the power that you get is for every photon that is absorbed, you create an electron and hole. If this electron and hole does not participate in any other process, but go to the outer circuit to drive you a current, then for every photon, you get 1 unit of current. But of course, the power is not just the current, but it's current multiplied by voltage. So if you make the band gap very small so that you absorb all the photons available to the solar spectrum, you get lots of current, but almost zero voltage, so that the product will become very small. In order to maximize the product, we know that you need an optimum band gap such that you can absorb a large part of the solar spectrum and also have a large enough voltage output such that the power is maximized. And that band gap that corresponds to this ideal value is in the order of 1.3, 1.4 electron volt. And since this was very close to that 1.5, 1.6 electron volt, he said, this must give me a very good solar photovoltaic. Unfortunately, all his attempts ended with very small percentage of efficiency, and nobody was looking at these papers. These papers couldn't get published. They were only being published in conference proceedings. Not only that the efficiency was very small, but also it was very unstable. I'll talk about that in a moment. Then he, with some effort, he pushed it up in 2009 to get it slightly higher. You can see about 3-4%, which got published. And then in collaboration with Namgui Park, they published in 2011, where he could push it up to 6.5%. Still, nobody took notice of it because it wasn't interesting, because solar photovoltaic based on silicon already had crossed 20% by that time. And so nobody took notice of it. Till two papers appeared more or less at the same time, reporting about 10 or slightly higher than 10% efficiency. One from Henry Snade's group and the other from the Namgui Park with Michael Gretz. And all hell broke loose. 10% was somehow the mental block that the photovoltaic community had, but once it crossed the 10%, everybody jumped in. And that is the time you should have gone for an MRS meeting or an APS meeting or an SS meeting. Almost all the symposia were devoted to that. Literally thousands of groups jumped into this, trying to understand and better the efficiency and get better properties out of it. Then it already very rapidly showed that it had some very interesting properties. But first, let me give you the idea. This is a very busy curve. You don't have to know everything. You can see different colors, different symbols. This is the timeline you can see, starting from 1975 to something like 2023. And these are solar cell efficiency. different color and connected lines, tracking different technologies of solar cell photovoltaic, how its efficiency is increasing with time. There are too many of them. The most common one that we know, which is commercially most successful, is the silicon-based technology. This is the polycrystalline silicon technology, and this one is the single crystal silicon technology. You can see that from here to here, going from about 14% efficiency, reaching about 26% efficiency with the single crystal, and here also starting from about 14%, reaching up to close to 24%. It has taken us almost 43 years for this very small increase. So it's been a very slow, tedious, and arduous journey. But that slow increase in the efficiency has been absolutely instrumental for making solar photovoltaic today a feasible commercial product. And it has now created electricity at a rate that is competing with the conventional sources, if not cheaper than that. And that is really driving this revolution that you are seeing today in solar photovoltaic application. 43 years of history. This material that I talked about in 2012, 2013, that we realized that it can give us more than 10%, starting from 10% to go beyond the polycrystalline silicon technology, has now crossed 25%. It has achieved only in 7 years. Nothing else has shown that kind of rapid progress, any of the technologies that is listed over here. And this is the reason why everybody thinks that this is really going to revolutionize the solar cell technology. Not only the solar cell technology, they have also, in the form of nanocrystals, are believed to revolutionize electro-optical properties, which I'll show you in a moment. So this is now being pursued very heavily. Why is it only the efficiency? It turns out it's not only the efficiency. There are many, many very important aspects of this particular material. For example, silicon is an extraordinarily poor absorber of photons because it has indirect band gap. It just doesn't absorb unless you put a very thick layer of silicon. And putting a thick layer of silicon has other technological difficulties because the electron and hole get generated somewhere deep inside. To pull it out to the surface so that it can go into the electrodes and drive an external circuit current to the external circuit is very difficult. So you have to purify silicon extraordinarily. Everything adds to the cost as well as the energy that you have to put in to fabricate those devices. These devices, this material, you can produce in a very energy cheap manner. Basically, solution processing at 100 degrees, 120 degrees, 150 degrees, you can make these in as various solvents, and you can coat this on anything that you want very easily with very little cost. Not only that, these are extraordinary absorber of photons, such that very thin layer of this material can absorb all the photons that's coming in, and therefore you can make very thin cells, and that is shown over here. This is what Michael Gretzel had introduced as a competitor to the silicon photovoltaic technology called Dyesensitized solar cell, which said that about 10 micron thick device is good enough. And systematically, this technology was evolving in extremely thin cells. But this active material that I just now introduced, the perovskite-based system, you can have sub-micron thickness, 0.5, 0.2 micron is good enough to absorb all the photons. So basically, the material cost goes down, your mechanical structure becomes lighter. So there are enormous amount of good things about it. Not only that, another very interesting thing that was discovered very early on, originally one thought that this technology is like dye-sensitized solar cell. What is a dye-sensitized solar cell? It's very simple. The photon is absorbed by the dye. Dye implies something very colored. The fact that something is colored because it absorbs a part of the solar spectrum, a visible part of the solar spectrum, very efficiently. And having absorbed, it creates an electron and hole, but the dye is normally not a very good conductor of the electron and hole. So what one did was to put titanium dioxide particles that are coated with the dye that created the electron and hole. The electron jumped into the TiO2 and got transferred to one terminal, and they put some other hole extracting material on the other side. It hole went to the other electrode, and that drove the electricity outside. And that's how one thought that this material also works. Very quickly, Henry Snaith found that actually if you replace the TiO2 with alumina, which is absolutely no good for conducting electron or hole, the efficiency didn't change, which meant that this dye material, this perovskite that I'm talking about, is also a very good conductor of electrons. And it turns out it also is a very good conductor, very high mobility for electron and hole both, such that the device architecture from this mesoporous TiO2 covered with the dye, it went on to this solid block of the hybrid material, which can then absorb photon, a very thin layer of it. And then you take the electron out this way, hole out that way, and that made the entire device structure much more simple. So basically, it revolutionized the way we think about solar cells. And what makes it so good, as you know, the silicon technology is basically based on a PN junction. This, let's say, silicon block, and you create a PN junction, such that depending on whether you create electron or hole here, absorb the photon here or there, what would happen, the electron will always go towards a plus terminal and hole will go towards the minus terminal, so that you can separate out the electron and hole and drive the electricity outside. So one of the important characteristic is how far the electron and hole diffuse on their own without getting trapped or annihilating with the other kind of charge carrier. And it turns out that properties of this particular material that we are talking about. So if good photovoltaic material should be very good absorber of light, I've said, it must give rise to very effective separation of charge carriers. So it should have slow recombination and long carrier diffusion length. And also it should have high open circuit voltage, because remember, we want to maximize the power, which is voltage multiplied by the current that it drives. And it turns out this material has nearly the ideal band gap, as I mentioned, 1.55, 1.6 electron volt. It has an extraordinarily high absorption coefficient. It has long carrier diffusion length. Electron and hole can diffuse long distances, and the open circuit voltage is very large, up to 1.1 volts. The question that we've asked very early on, around 2013, 2014, is that are there any fundamental questions that one didn't understand? And we looked at the basic issues that again, related to what makes it so good, because there's a question of whether there's ferroelectricity. Now, the reason one thought about ferroelectricity in this material is that this Ma unit that you're putting in, CH3, NH3, because you have a carbon and nitrogen which are dissimilar, which means it doesn't have an inversion symmetry, so it has a dipole. So the question one asks, what does this dipole do? Every unit cell has a dipole. Do these dipoles arrange themselves in a periodic manner in a ferro way, all the dipoles pointing same way? Because if it did, then it's a polar material, and it could also be ferroelectric and switch it by applying a voltage, and that would then help in separating the electron and hole, because the electron will try to go to the one end of the dipole, one end of the macroscopic dipole of ferroelectric material. The hole will try to go to the other end, so you will separate out electron and hole very quickly. Or if it does not order, then of course there are other questions. So it is really a question about dipoles, and it can be ferroelectrically or antiferroelectrically or paraelectrically disordered state. If it is disordered, it could be static or dynamic. So all these questions are very important to understand the properties. And a more fundamental question than ferroelectricity, as I said, whether the structure is polar or not, whether all the dipoles align in a particular way. And there's also the very important question about the excitonic binding energy. The excitonic binding energy refers to, I told you that a photon, when it gets absorbed by a semiconductor with something with a band gap, you create an electron in the conduction band and hole in the valence band. If these two, of course, being oppositely charged, attract each other, the energy with which they attract each other is the exciton binding energy. This exciton binding energy, you want it to be small or comparable to the thermal energy, such that you can split it apart. Because if it is very strongly bound, then the electron and hole are not going to get separated and will not get the electricity outside. So it's a very important criteria to have the exciton binding energy small. The question is it small or large? Because unfortunately, the estimates run from 2 to 100 milli-electron volts, which means that we don't have any agreement and one doesn't know what the excitonic binding energy. These are the kind of questions that we asked early on. This is the background of the three-dimensional objects that I talked about, the excitement of it. And several people contributed. Mainly, this is being the background, I'll just quickly go over it. These are people that contributed very significantly with my also collaborators, Anshu Pandey, my colleagues, and Guru Rao, and here from JNCSR, Professor Sundarshan and Professor Narayan's group, And from Vienna, we have Cesare Fancini and Georg Kresse, and that person, it was mainly Menno who contributed to that. Also, we collaborated with them. So it was initially driven mainly by Sharda and Bhushan. Then later on, Ashutosh also, who's now at Los Alamos, contributed very significantly. We showed that it's extremely, first of all, that it's not ferroelectric material. The dipoles are disordered, they're dynamically disordered. And the fact that we always thought that these organic molecules don't matter for the physical properties of the inorganic cage is also completely incorrect. And these are the things that we had addressed. But I'll not be talking about that today. I'll now come to the question of why do we need to talk about two-dimensional systems. Now, this is a three-dimensional object, right? I mean, as I said, these octahedra connected are running in all three directions. How can I derive a two-dimensional structure out of this? Think of it this way, that these are sitting in the middle of it. And one more important thing that let me tell you, this is where the electro-optical and optoelectronic properties come in very handy. What I'm showing you is UV absorption spectrum. If you don't know about it, you don't have to worry about it. All that it does is to tell you that this is the energy scale. If you like electron volts, 1200 divided by the number that you see is the band gap where you see a sharp rise. 800 would correspond to 1.5 electron volt. 600 would correspond to about 2 electron volt. What we are doing is making the MAPBI3 compound and replacing iodine systematically with bromine. And you can see that the band gap, this sharpness rise, is systematically changing, starting from 1.5 electron volts to greater than 2 electron volts, which means that the band absorption edge is shifting through the visible range, right from red all the way to somewhere near green. And then by bringing chlorine also, I can drive it all the way to blue, which means that the optical property of this material can be tuned all right across the visible spectrum, and therefore you can get all kinds of properties, optical properties and electro-optical properties. And people are making light-emitting diodes from these materials, and it's believed that it might yield some very interesting results. So suitable band gap is an exciting aspect of it, and the fact that you can engineer the band gap for the purpose that you have in mind. It has very low excitonic binding energy. I told you that why we need low excitonic binding energy. If the binding energy would be too large, then you cannot separate the electron and hole, and then it will not drive the current outside. The iodine compound, you can see this break is because there's a phase transition, is in the order of 30-35 milli-electron volt. The bromine compound around 60 milli-electron volt, which are comparable to the thermal energy scale. This is about twice the thermal energy scale. So e to the power minus half is still not a very small quantity, and you'll be able to drive the photovoltaic cell even with an excitonic binding energy of that. So if this is so good, why are we worried? Why do we need to go to the 2D system at all, or think about them, forget about going there? It turns out that it has one awful aspect, the environmental stability. I told you, Miyasaka couldn't publish for a very long time. The system was so unstable. Within minutes, it will degrade. What is being shown over here, again, UV absorption curve. When you make the system, the material, you have a band gap near 1.5 electron volt. 800 nanometer, I told you, is 1.5 electron volt. As time passes, you can see that it gets shifted, and this is PBI2. The system just degrades into PBI2 in presence of moisture. And moisture is inevitable. And I don't have to convince you in Calcutta about moisture. So that really destroys the device very, very quickly. And you need to think about this stability. And that is what brings us to the 2D. Why? Now, think that this is the ABX3 structure that I told you about. This is A cation sitting there, which in our case was an organic molecule, small enough to get in there. Now imagine that I want to drive in a much larger organic molecule there, and I make it energetically suitable for it to interact such that it wants to get in there, but there's not enough volume available to it. Then what it might do, if the interaction strengths are right, is to split open the system here, take this layer out like this, accommodate itself, put the next layer like that, accommodate itself, put the next layer like this. So you are really taking scissors and cutting it off along these points and spreading them up, creating from the 3D structure a 2D structure. And this is the two-dimensional structure. Why should we think about it? Because now I told you that in this position, we can only fit in most of the time only two organic molecules, Ma and Fa. But once I've cut open like this, as long as the interaction at this end and that end are sufficient to cut open, what I do in the middle is up to me. And so I can make all kinds of organic molecules to accommodate them in there and change its properties by choosing the organic molecule. For example, I can put a hydrophobic material there, hydrophobic, so it will repel the moisture. Moisture will not come near it, and so I may be able to make it extremely stable. The stability is an issue for the 3D compound, and this holds out the telltale possibility, tremendous excitement that I might make it more stable with respect to moisture and also tune properties the way I like. But what is the price that I would pay? From now, you realize that now I have a huge library of systems because I can put almost anything here. And so I have the possibility number of compounds, whereas here I had only Ma and Fa. I have all the kind of organic molecules can be put here. So we have many, many properties to explore. But what price do I pay? This again is systematic because actually it's even more exciting than that. I only talked about that you can put molecules here, split it open, but that splitting open can be in two different ways, with one organic unit that couples at both ends. So think of it as two-headed object. One head will couple to this, other head will couple to that. And then you can see that this inorganic unit and that inorganic unit will be exactly above each other. But if you have a single-headed organic molecules like this, then it will split open there, that will split open there. But these molecules will try to interdigitate themselves for energetic reasons, and therefore they'll stagger each other with respect to this one will be shifted with respect to that and give rise to another structural family. This is called Rudolfson-Popper series, and this is called the Dion-Jacob. So there are two different kinds of structure. So already you can see that you are going to get different properties. Not only that, instead of having one layer, you can have two layers of inorganic compounds separated by two layers, 3 layers, 4 layers, 5 layers. So you have tremendous amount of possibilities that come up, each with its unique properties, and you can design the properties the way you wish. So that's the excitement. The price that we pay, let's think about this structure. So what does it look like? It looks like an inorganic unit with organic spaces in between. This one and that one have very different dielectric constant. They don't have covalent bonding. That's only hydrogen bonding. So all the electronic structure of this inorganic unit in the 3D case was 3-dimensionally delocalized. But now it will get 2-dimensionally delocalized. And a third dimension, it will get quantum confined. The moment you quantum confine the system, the band gaps will increase because of quantum confinement. And band gap is a very important criteria for all the applications that I'm talking about. And if my band gap increases on uncontrolled manner, then that is the price that I'm paying. Not only that the band gap will increase, now that the dielectric confinement is there, because this has a very different dielectric constant than that one, electron and hole will only be able to delocalize in 2 dimension rather than in 3 dimension. Therefore, the excitonic binding energy, which goes as 1 over epsilon squared, will be increasing significantly. And it turns out that many of these compounds that people make, there are 3 examples cited here, have their excitonic binding energy more than 100 milli-electron volt compared to the 3D counterpart that I told you in the order of 30 milli-electron volt or 60 milli-electron volt. And that's bad news, because both the band gap increasing and excitonic binding energy increasing are the prices that you are paying, with the hope that we'll be able to design something that will have the stability with respect to moisture. So that really is the background that brings us to talking about our experience in trying to play around in the low-dimensional hybrid halide materials. We have really realized many different interesting properties, ferroelectric properties that I'll not talk about. I'll talk about this in a moment, and this, as I said, so mainly I'm going to talk about this particular one, how we go about designing the lowest band gap and excitonic binding energy. It turns out that we have been able to get a material that has really the lowest band gap and lowest excitonic binding energy while being extremely stable with respect to moisture, one of the highest stability in moisture of this class of material. And that's the main story I'm going to talk about. And then later I'll come back to this where this strict confinement in terms of dimensionality that gets blurred, as I have pointed out. So that brings me to this topic. And this is actually driven by this extraordinary student of mine, Devashmita, who has finished her PhD and is still there, but soon should be going for postdoc. I've always been extremely fortunate in having wonderful and extraordinary students who drive our science. And it's really gratifying to work with all these young people. So Devashmita collaborated with several people in IISc, my colleague Abhishek Mandal and his students, and Professor Guru Rao and his students. The calculation comes from Arup and Filipov. Arup is now faculty at IIT Hyderabad. My colleague from Sense, Pralay Satra, and my colleague Shaibal and his student from IIT Bombay. We patented the material because it's very exciting. That was beginning of January, and this article has just appeared last week as an ASAP article. The organic molecule that I said that you can stick it in for some reason, this is the molecule that I'm going to talk about. Of course, we talk about the successful molecules. Devashmita tried some 20 odd with a certain design principle. The design principle is simple. I'll just explain to you. The reason we were taking this kind, you can see there's a huge lot of delocalized electrons here, resonant structures, which our hope was that these will provide response to the electron hole generation. Basically, the dielectric constant of these materials will be such that it will provide screening. So we were hoping to lower the excitonic binding energy. It turned out that in preparing this, so basically you do something to this head and that head, you protonate them such that this can now go and interact with the inorganic material. So as I said, the head must have an affinity for the inorganic cage for you to be able to split open the inorganic layers. But this one, which we wanted to be delocalized, turned out to be also protonated, so it stopped being delocalized. But it turns out, as I'll show you, that it played a very important role in the properties that we get. This is just a picture of beautiful crystals that you can make from this material. This is called APD, azopyridine, essentially. And this is a crystal structure. So you basically get these inorganic layers separated by these organic layers. I'll not belabor the point that there's a structural peculiarity of this. It's a two-headed molecule that you have taken, and yet this layer is staggered with respect to that one, which I say normally is realized only with one-headed organic molecule. But I'll not go there. But that plays a very important role in determining the properties of this. And I'll show you later that it is essentially because this iodine wants to have a hydrogen bonding with that one and with that one. And that's the reason this molecule tries to go in a tilted manner, staggering the two interlayers. And by doing that, the layers come closer together. And that leads to an interesting decrease of the band gap and plays a very important role. And this head forces itself into the inorganic layer to maximize the hydrogen bonding. And that plays a very important role. That's the crystal structure. We don't have to spend more time on that. The band gap. Let us talk about the band gap. This is the absorption curve. And I told you the absorption curve gives me an estimate of the band gap right in the beginning. You can see two peaks here. This is the exciton formation, and this is the free carrier generation absorption edge. So basically, if you extrapolate this edge and find out what its energy is, you can find out what the band gap is. And that is what is done in this plot. And turns out that the band gap of this material is about 2.19 electron volts. How does it compare with the other materials in this class of 2D material with single layer of inorganic units? That is shown over here. These are all the published data from different molecules. The red and the blue are these two different classes of doing it. One is these are two-headed objects, organic molecule. These are single-headed, but that's unimportant for you. So, and this is the band gap plotted of all these molecules, of all this two-dimensional system. And the one that we have made is the lowest band gap of all the molecules, of all the systems with different organic molecules that you have realized. Now, in order to trying to find out what really ticks, why does it have the lowest band gap? Which structural aspect? Because eventually it is structural aspect, because all of them are PBI4. You can see the inorganic unit is the same. It is the organic unit that is changing, but the organic unit does not directly control the electronic band gap. That's the property of the inorganic unit. So it's something of the PbI4 that is changing because of the organic, and that is changing the band gap, right? And that, it turns out that it is the PbI-Pb angle that controls largely. Other things also influence, but the most important influence comes from the PbI-Pb angle. I told you that there's an iodine that is shared between every 2 Pb. That angle, if it is absolutely straight on, we understand very easily then the electron can hop from lead to iodine to lead very easily. As that angle bends into away from 180 degrees, that hopping becomes less efficient, less facile, simply because the symmetry of the wave function that allows you to hop from this side to that iodine side is not exactly the same symmetry that will allow you to go from the iodine to lead. So effectively, the hopping between lead and lead becomes smaller, so the band width decreases, and when bandwidth decreases, the band gap increases. And that is exactly what you're seeing as I approach. That is the ideal. You cannot get more than 180 degrees, because going from a smaller angle, if you keep going there and you get 180 degrees, you try to make it, actually you're getting a smaller angle. So that's the largest angle you can get. And as the angle, you can see as we approach, it is approaching, the band gap is decreasing. And fortuitously, we have been able to get the only example of ideal 180 degrees realized in a PbI-Pb angle. And I'll come back and talk about why this one gets to this 180 degrees in a moment. But before that, let's talk about the excitonic binding energy. Another point that I've talked about. So this time we need to do the experiment in a slightly different way. These are true absorption experiments on a thin film, as shown over here, as a function of temperature. And it turns out this is the excitonic absorption, and this is the free carrier absorption. And you can fit them with a model called Elliott model, where the excitonic binding energy is a parameter. So from that, best fit tells you what the excitonic binding energy is. It turns out how you extract excitonic binding energy, which technique you use, it changes a lot. And in fact, photoluminescence and other things have been used. We believe the absorption is the best way. So we are using the absorption to extract the excitonic binding energy. And these are the fits of how we do. There's a free absorption, and this is the excitonic absorption feature, and that gives you the excitonic binding energy. Look at the excitonic binding energy. It's in the order of 48 millielectron volt, which is much, much smaller than the values I was showing you earlier, more than 100 millielectron volt. To compile all reported literature data using absorption experiment, which are these blue dots at different temperatures, this is the excitonic binding energy scale. Ours is the lowest excitonic binding energy of all these 2D materials. That you'll find 7, seems to be lower, but this is photoluminescence. The same one with another technique comes to a higher binding energy, and that shows you the dependence on the technique. So if we stay with the absorption one, there's absolutely no doubt that it's the lowest excitonic binding energy that we have realized. The reason we get this 180 degrees, which actually is at the center of both the band gap being lowered and excitonic binding energy being lowered, is because as I told you, that this iodine wants to enjoy 2 hydrogen bonding, one with this one with that one. In order to enjoy this hydrogen bonding, this head of the organic molecule has to penetrate into this inorganic layer defined by the iodine layer. So we ask the question, how much can I push it in? Can I push in further? This was realized by calculation, by varying in the c-axis the dimension and allowing the AB plane to adapt for energy minimization, and that is shown over here. This is the actual distance that the system wants to be in, which is the lowest energy. You can expand it or you contract it. When you contract it, you are trying to push the head inside. When expanding it, you are trying to take the head out. This is how much the N atom penetrates into below this layer. When it is expanded, it is above the iodine layer by this much. As I approach the 180 degrees angle, or the c-axis gets a correct dimension of c-axis, very quickly it's penetrating, but once it comes to the optimal geometry, it hardly penetrates anymore. Simply because now the electrostatic interaction between this head and the inorganic cage becomes too large, not allowing it to penetrate anymore. So if you scratch the c-axis further, all that it does is to tilt itself, retaining the penetration about the same, and that is reflected over here. And in order to accommodate this up to this point, for it to get in, the PBI-PB angle has to expand because the head is trying to get inside this cage defined by the iron molecule. So in order to accommodate this head sticking its nose in, the PBI-PB angle becomes 180 degrees. And that is what we have realized. Well, I've talked about that we have got the lowest binding energy and lowest excitonic binding energy, lowest band gap and lowest exciton binding energy. What about the stability with which I motivated you right in the beginning? It turns out that it's also extremely water stable. This is MAPBI3 film, which looks black. Dipped in water, you know where the water level is. Within seconds, it turns into PBI2. This is the material that I talked about, APD PBI4, and dipped into water. There's absolutely no change. This is, of course, visual, but one can characterize it by looking at the photoluminescence before and after immersion. And to convince the disbeliever, you can see that they're identical. One falls on the other. So it's extremely water stable. It turns out that the best stability that was reported in the literature before in a JACS paper in 2018 or 19, where they said that they can dump the crystals into water and it takes 15 minutes before it begins to form PBI2. When we dump this into the water, it takes more than 4 hours before it begins to show PBI2. So it's extraordinarily stable. But all this stability, all these good results, does it translate into good photovoltaic property? And in order to check this, we have not really explored this completely, but initial results that we forged by the reviewer that we had to include is that where we included this APD ligand while making the photovoltaic cell, and it turns out that the red shows without the APD molecule and the blue shows with the APD molecule. There's a control with respect to that. The current density goes up, the voltage goes up. There's something else that's called fill factor, which actually becomes a little worse, giving me still an efficiency increase of the cell when I use the APD molecule. But it was the main motivation was to make it more stable, and that is shown over here. Normalized efficiency as a function of time. If I don't use the ligand, in this particular case, it decays that rapidly, whereas if I use the APD molecule, then it's a lot more stable. So let me summarize this part of the talk by pointing out that I have shown you a very unique compound with a PBI-PB angle of 180 degrees and explained why that comes about. And I've shown you that it shows the lowest band gap of all materials in this class, lowest excitonic binding energy, very high water stability, and also stability in a device structure. If I may get 5 more minutes, is that okay? So I will give you the last example that I talked about. This is an example where what we did was to take a chiral molecule. Again, we are trying to make a lower dimensional system, not a 3-dimensional. So I have to choose a largish organic molecule. So we ask the question, we are going to have a chiral molecule. Now, a chiral molecule, if I can take a R or S variety. And if I can make a single crystal, if these molecules are properly ordered, the crystal structure will be chiral, simply because their organic molecule is chiral, and that will make sure that the system is chiral. But the question really is, can the chirality of the organic be driven into the chirality of the inorganic part? Now, what do I mean by that? Well, or how do I test it? The testing of the chirality is very simple. You do an absorption experiment with right circularly polarized light and a left circularly polarized light. If the system is chiral, the absorption coefficient is not quite the same. And so you look at the difference between these two absorption, and that measures how chiral your system is. And now the organic and the inorganic, as I told you, have electronic structure vastly different. The organic in general has a very large band gap. This has a very small band gap. Normally, you cannot say a band gap of this and that when you make one compound, because the compound says it has one band gap. But the fact that this is not covalently bonded to that, you can get clear signature of this and clear signature of that, that are distinctly separated over a large energy range. And then you can ask the question, do I see the absorption feature of only the organic chiral? Inorganic not, inorganic part not, the part of the absorption that's dictated by the inorganic electronic states, or it is. And if it is, what makes it chiral? how does the chirality get translated from the organic molecule to the inorganic molecule? This is a question that intrigued us, and that's why we went into this particular project, trying to understand for ourselves. And this is driven by yet another really wonderful and extraordinary student, Ranjan Das, who's also the same batch as Deboshmita, who did the previous work, and he's also finished his PhD, waiting to go somewhere. And there's again a collaboration, and Diptikanta helped us, Dr. Diptikanta helped us with the crystal structure. Calculation again comes from Arup Mahata and Filippo's group, and in sense, Pralay Satra and his student helped us. And there's a paper that came out in publication a couple of months ago, just about 2 months ago. So this is the molecule that we are taking, which is a chiral molecule. And we can do it, the compound only with this or only with that, so that I get a chiral system, and both crystallizes, of course, in a chiral space group. That is trivial. It will have to do that because you have a chiral molecule to start with. That's not the interesting part. The interesting part is, can I get the chirality transfer? Now, this is only the molecule. If I look at its chirality, the absorption of the R and S variety, the two different chiral system, they're of course identical. But if I take only one of them, let's say R, and take the difference between left and right circularly polarized light absorption, I see a distinct feature that measures the difference between the right and left circularly polarized absorption. And I see a mirror image of that if I take the opposite chirality. And what I would like you to notice is that this organic does not absorb in longer wavelength than 275 and 290. If I see anything on that side, that is contributed by the inorganic part when I make the compound. So we know that chirality coming, let's say below 280 or so, is all because of the organic. The question is, do I have chirality there? Now that's the result over here. This you can see. Now look at the wavelength. It's actually some 350 to 700. So it's starting from there and going far that longer wavelength. So these are states which are completely inorganic dominated. And those states have this huge CD, depending on R or S variety. And there's a way to define this CD to be sample thickness independent, and that's defined as GCD, so that you can compare it with across one material to the other material, and that GCD value at the maximum is 1 × 10⁻². At a wavelength which is orange red, this is the world's record chiral parameter GCD in this range for any hybrid material. So not only the chirality is transferred to the inorganic part, but it's transferred with vengeance, with making it extremely chiral. And so one would like to understand what leads to this chirality. And as soon as we look at the this giant GCD, we understand why it happens by looking at the structure. Now the structure should be plotted over here, and you can see that these are copper bromine 4 tetrahedron, and these 4 bromine are not shared with the next copper. So these are not corner connected that made the 2D object. These are isolated copper bromine 4 units. So these are zero-dimensional object. What is the advantage of a zero-dimensional object? A zero-dimensional object can be rotated easily because it's not connected. Imagine if they are sharing, if I try to rotate this one, either I have to rotate the whole crystal, which will not be chiral, but if I rotate this one, if I have to rotate the next one even more, I'm really playing around with the angle, which cannot be changed so easily. So it becomes very difficult to transfer chirality when you have these connected corners. And that's why they don't show large chirality. Zero-dimensional objects will show you huge chirality. So immediately we understood that this to that, there's a screw axis that is established because of the chirality of the organic. So the organic holds the copper bromine 4, rotates them as we go along that, giving rise to arrangement of the copper bromine 4 that becomes chiral. So the electronic structure of the entire copper bromine 4 becomes chiral. That is wonderful. And then we come back and say, okay, yes, that's the zero-dimensionality makes it chiral. But then the surprise comes that the energy range is huge over which the system is chiral, and it seems to be continuous. If it is zero-dimensional, then there should be no bandwidth associated with that, and I should see sharp features. But I find that they're very broadened feature, which tells me that it's not zero-dimensional in some sense. Then we go back to the structure again, trying to understand that, because it's such a surprising thing about a zero-dimensional system, and this is where the importance of being weakly two-dimensional comes in. You can see these are the copper bromine 4, and these are the 0D that I was talking about. So each of the organic comes and rotates them a little bit. So the orientation of this is not the same as the orientation of this. And then it comes back here with the same kind of screw axis. But this bromine-bromine distance is very short. It's shorter than in copper bromide. And so it is the halogen bonding that sets up a bandwidth of this material. And not only that, makes the rotations coherent, these short connection. And this short connection, you can see, then makes a one-dimensional object starting with this zero-dimensional object. And this one-dimensional object with the next one-dimensional object has a slightly longer, but still an halogen-halogen bonding that gives rise to a weakly 2D structure, giving you the dispersional width that you're seeing. So that brings me to the, let me skip this part. Summarize once again for this part, that it is the 0D-ness that allows me to very effectively transfer the chirality to the inorganic unit, but it is the 2D aspect that allows me to broaden and in fact shift the bandgap to even lower energy, making it the most chiral in the orange-red part of the visible spectrum. With that, let me thank you for your attention. Thank you very much. Let me get to the best part. You want this one? That was okay?
Yeah, that's fine. So I'm just trying to see what is the incentive for the molecule and the structure to have this configuration versus shifting laterally and being straight as many other structures.
Yeah. So if it was straight up, you'll not be able to get this. That of course doesn't work. So if you hold it straight, this guy will be straight, which means this will be far up and you cannot get this hydrogen bonding.
So that
to get this hydrogen bonding, the molecule wants to tilt. So it is for this molecule, it wants this hydrogen bonding and this hydrogen bonding, both. To get that, it has to come inside, which makes it 180 degrees, and tilt because it cannot go sufficiently inside.
So the blue molecule left to the blue atom left to that is what?
This is nitrogen hydrogen.
Yeah, and then left side.
This is also nitrogen hydrogen.
Yeah, but I'm saying the one. Let me just say this one. This is what? This one?
That's a carbon.
Carbon. So then I
so
understand.
the gray ones are carbon. Yeah. These are the amine group.
Okay, then I understand.
So that's why it needs to tilt and push in simultaneously.
Any other question?
Okay, Didi. I have two questions. The first one is that, out of the two different things, RP and DJ that you mentioned, the one which seems to be the most favorable for the purpose of optimizing both the excitonic as well as the minimum bandgap. Now, I just wanted to know, do you have an idea as to what is typically the binding between the two inorganic layers interspersed with what is typical order?
Hydrogen bonding. So it's in the order of hydrogen bonding. This tied to that only via hydrogen bonding. So essentially the electronic structure of this is decoupled from that largely, which means that the crystal structure in this direction, the binding comes from these hydrogen bonds. So it's in the scale of hydrogen bonding.
Okay. But just now what you said that interpenetration and things like so you are trying to tune that.
Yes.
So obviously then whatever be the binding energy between the two layers, that also gets sort of
Sure, absolutely. That is, in fact, the reason we believe that it actually, because bringing this closer, that was part of the design of the molecule that we were doing. So the idea was to have a lot of delocalized electrons so that the organic itself can provide screening, as well as keep it short so that the separation between them is smaller rather than larger. So these are the two design principles with which we chose the ligands. And Devoshmita chose some 20-odd ligands, out of which one has worked. Most of the cases, you don't even form the compound.
I see.
Or it forms in one-dimensional or zero-dimensional objects.
So
there are other.
So RP is something which is not really.
It's not the essential aspect.
Okay. So the second question is about it's a more general question. The entire thing, whatever you discussed in the 2D, is based on lead. Is there a possibility that if you, I mean, we know all that replacing lead with something like tin?
Yeah, that's a lot of work that is going on there, simply because lead has this standard problem of being toxic, and so far, even in the three-dimensional, the tin has made very rapid progress, but it's still, if I remember right, I've seen in recent times a spectacular report, but the efficiency is up to 15%. 15% and 25% are very, and in fact now tandem cells with these lead based with silicon has crossed 33%.
Yeah, but by doing this kind of a tailoring, suppose you do with tin and you try to do the tailoring like this.
Sure, it would be very interesting. It would be, there are so many possibilities that I wish that there are many more students who can drive this, but we're limited by the number of students. So, I mean, Devashmita is looking at some other variations, some other ideas that we have, using similar molecules rather than going to tin, because that would be changing their basic electronic structure drastically, and you have to relearn many things. That I would love to start with a young student whose entire PhD would be on that, and it would be lovely to be able to do that. But I don't have the possibility of doing that right now.
Thank you, Didi. It was a fascinating talk, as always.
That's why I have all his friends in the audience.
I also have two questions. The first one, looking into the structure, is the inversion symmetry broken here, and ferroelectricity is not possible?
It's not ferroelectric.
Okay. The second question is a little bit surprised that in the two-dimensional form you have so low binding energy, excitonic binding energy. Do you have more fundamental understanding why the binding energy decreases so much?
I really believe, because see, the delocalized electron in this part remains. I don't have the delocalization here anymore because that's got hydrated, protonated. But the delocalized, and this sticks its neck in. So it's in the very close vicinity of this cage, the inorganic cage. And I believe that this actually provides a lot of screening. Because if you create an electron hole there, this would, just by Coulomb interaction, I don't have to have covalent interaction, by Coulomb interaction, if it is close enough, and since Coulomb interaction is long range, that will respond very quickly. And it is the trick of having a benzene ring coming close to where the electron hole are getting generated. That is what is, I believe, giving rise to the lowering of the exciton binding energy. Of course, a BSc would be the ideal approach to understand the microscopic origin, but do you know how demanding that is?
So in that sense, it is close to a 3D structure where...
not 3D, but at least it's not completely. Dielectric mismatch is somewhat reduced because of this delocalized part, which has come close to it.
Thank you.
Great talk, Didi, as usual. This is a stupid question. So
those are the ones I'm most scared of. They can kill you.
No, just a curiosity related to what I was saying. People have just asked. If it is stupid, just say. Do you want to say something about possibility of multiferroics? He talked about ferroelectricity, and you know this problem about why we cannot get multiferroics, right? It's a symmetry argument, and I was thinking that you have found a way of introducing chirality to solve.
Why do you think I was working with copper and chiral molecules?
Okay, but is there a future?
We're struggling with it, and in fact, we're looking at it very, very carefully, because it would also be even more interesting than just multiferric, but because it's also two-dimensional or lower dimensional. And so, but that itself, the copper example that I've given you, our motivation was exactly there. The chirality and copper put together. It turns out that the copper chloride sample, I was writing a paper on that right now, but I'm so preempting a little bit of what we're doing. There's something very exciting. But that turns out to have magnetic interaction that's almost zero. So it doesn't magnetically order. So I have a paramagnetic system. Down to 2 Kelvin, we can see. And down to 2 Kelvin, if I extrapolate the Curie-wise temperature, which gives me an idea about the interaction, is also very close to 0. Simply because the chlorine-chlorine distance is much larger. And I told you the bromine-bromine distance is surprisingly small. And the bromine compound has an antiferromagnetic transition in the order of 7 Kelvin or so, very low. But the bromine compound is not ferroelectric, whereas the chloride compound is ferroelectric. I didn't tell you that story. And that's a paper we are writing right now. Now the question is, so we are looking at, with that knowledge, we are looking how to design such that I can enhance the magnetic coupling, but keep the ferroelectricity. And then ask the question in a chiral, ferroelectric, magnetic, two-dimensional system, what kind of physics plays out? And we are trying for that. So in this particular system, we have realized ferroelectricity without the magnetism, and we have realized the magnetism without the ferroelectricity. I just got to look at both. Well, yeah, we've also done in some way this, and it has given some other story, which we are just will be communicating very soon. It is antiferromagnetic, the copper, because it tends to. Now we also have some ideas of making it ferromagnetic interaction, and there are some examples that we have in mind, where because see the super exchange tends to be antiferromagnetic unless you get the angle down to a very small angle somehow. There are other tricks we can do. So we are looking at systems that will have orbital ordering such that the magnetic spin sector can afford to have ferromagnetism. So that you still can open up a gap, because you need to open up a gap. The motivation for making this antiferromagnet also is to open up a gap so that you can stabilize the system. So you allow the opening up of the gap or the doubling of the periodicity coming from an orbital ordering and release the spin to behave ferromagnetically. So there are many different cute ideas that, but you try 200, maybe one will work, and then we'll be happy. If it does, go home, enjoy.
Okay, I was just trying to ask you that the weakly two-dimensional is becoming, right? Whether you can control the strength, but you have given some partial answer that chlorine
and bromine.
distance is very large.
Yeah.
So that must be very weak in that case.
Yeah.
What about iodine?
Iodine you cannot make. That's where, Sugata will tell you, copper iodide cannot form for a very good reason. There's a very, very good reason, because the D level and the iodine levels are such that will go into the form copper 1+. So that's why copper iodide will not form.
So with chlorine, it's not.
Bromine is a limiting behavior that you can
get.
get.
So chlorine is not even weakly two-dimensional?
Chlorine is very zero-dimensional. It depends on there is always the interaction never goes to 0, right? So this dimensionality that we are talking about is always an approximate statement. So it depends on which property you are looking at, depending on that, right? Sure. So the band dispersions are much more flat in the chloride compound than bromide compound.
Okay, so you said that zero-dimensional, then you have thrown a chain, one-dimensional.
And then it's a hierarchy of thinking about the electronic structure. Yeah. And you can see that the dispersion, if you look at in this direction, the dispersion is more in that than in this direction. And in this direction, it's 0 almost, completely flat. Because in the vertical direction, you're separated by the organic units. So you can see this hierarchy of dimensionality or the connectivity very clearly in the band dispersions.
Okay, thank you.
This antiferromagnetic ground state is interesting because, for various reasons, including, even the multiferrocity context, the work by Nicola Spalding on canted antiferromagnetism, ferromagnetism coming of canted. And
we are looking at a few such systems.
Could have your coexistence with ferroelectricity.
Sure. We are looking at such systems. The magnetic moment will be small, but you can still have it coupled. And because of magnetocrystalline anisotropy, that's the design principle there. Yes. And we are looking at some of the systems. Yes. I only talked about one, the orbital ordering, but you can also do it this way. Yes. And the third way of doing it is trying to get to 2 dissimilar transition metal ions.
Yes.
so that even the super exchange can be ferromagnetic, which will give you the strongest ferromagnetic, keeping it insulating. You need it insulating because otherwise ferroelectricity is not there.
Yes.
So you can use, so that's a double perovskite or its analog is another way that we're looking at it. So there are three different ways we are approaching the problem.
Many things in this molecularly engineered solids.
So we just need about 100 students.
Any other questions, students? Yeah.
Sir, very nice now.
Thank you.
So once you move from 3D to 2D by introducing large molecules.
Yeah, because I'm used to my voice,
Hello. Now I'm loud.
Yeah. Go ahead.
So once you move from 3D to 2D by introducing large molecule in between the two inorganic layers, so how the structure gets stabilized? Because you are saying that it's a hydrogen bond, binding in itself. So it's basically we see weak, very weak. So how the structure gets stabilized? Can you explain?
Yeah, basically, see, the point is that I should go to, let me see if I can quickly go to the schematic that I had drawn and then explain to you in a moment. Yeah, the previous two. So basically is, okay, let me get the full screen and then you'll know what I'm talking about. Okay. Okay. Come on. Oh, the wrong direction. Now it will come. Okay. To form this, as I told you, the structurally it won't be stable unless I put the yellow dots. Those are the ones that go to the cube center and stabilizes the structure. I told you that I'm going to put long molecules here to split it open. But that it's not the interaction of that long molecule alone, but the fact that this is not there. There's nothing to stabilize this 3D structure. Right? So the 2D layer can form, but in order to make the 3D, I need these yellow ones to stabilize the structure. So when I don't put at all any yellow dots, put only the long units, I get this. But if I now control the ratio of this to that, I get different number of layers.
Yeah.
That's how you try to control it. It's more easily said than done. When you try to make these, it's extremely difficult to get pure. Because there's nothing to say that you'll only get this 3 layer, not get a combination of 2 and 4. Because that also will stoichiometrically be the same. And so that's where the synthetic ability of the person doing comes in, but it's controlled by this to that ratio, which in this case is 0 for that. That's how you stabilize it.
One thing you have mentioned many times.
And as I said, sorry, to finish that, if you have this in excess or the interaction is very strong, then this will break this open and make it into 0-dimensional or 1-dimensional objects. So you have to really tune the interaction of this with that.
Sir, you have mentioned the localization of wave function. For inorganic, it's a delocalized, and for organic, it's a localized. So at the interface, is there any role when the excitonic binding?
No, I'll not say one is delocalized, the other is localized, because that will give the impression that one is metallic, the other is insulating. Both are insulating.
Okay.
Whether it is more confined in the 3rd dimension, if we make a 2D structure, the wave function doesn't extend in the 3rd direction too much. It becomes a pancake confined in the 2 dimension. The other case, it's confined in 3 dimension. Okay, it's confined in both cases, but it's a less confined than the pancake. Okay?
Thank you.
Sure.
Related to this question, I have just one question. So in your case, it's more confined into 2D, right?
Yes.
Not interacting with the layers.
Much weaker, yes.
Yeah. Because I can see even you have a conjugated organic molecules, but their conjugation is breaked at the middle.
Exactly, that we didn't want. And in fact, it came as a bad shock to us, because by design, we had kept that conjugation in between to have it to talk across the layer.
Exactly.
Our idea was to couple the 2 inorganic layers with that trick.
Yeah.
It didn't work.
Now the thing is whether there can be a design principles with something where the layer can be in like a the interacting,
Would be lovely.
and your wave function will be more dispersed.
Yeah,
Not
it will
only
be
like a
lovely.
2D, it will be like a 3D.
As I said, that was our motivation to choose this molecule, but it didn't live up to our expectation, but gave us some other nice result.
Yeah, although one thing, like now, if you do not have the long conjugations of the organic, whether the wave function can be in the 3-dimensionally dispersed, even the bending doesn't matter, right? If you have like a cyclohexane without like, like
Yes.
any kind of, maybe some kind of a vulnerable attractions and other
It's
dispersion
not
could
like
be.
benzene, of course, one carbon is replaced by
yeah,
nitrogen, but
exactly.
whatever that
But
is.
then a cyclohexane like a nitrogen, that should work in the same
I
way
guess
as
so.
well,
I mean,
right?
my organic chemistry knowledge is limited to chems 203, no, 102,
Yeah.
which was in 1973, January to April.
Okay.
I got an A, but I have not retained it across so many years. It's 50 years exact, more than 50 years now.
Okay. Thank you. Thank you.
So I think all of you will agree that it was a very, very, illuminating talk by Didi the Great. Okay. Thank you, Didi, for such a wonderful talk and details.
Thank you.
So we
Thank you.
conclude this session now. Thank you. Shobhita has something.
And now he can curse me. Now he can curse me.
No, there is something I just, this is just, the recording has stopped. So this is now social session. And I just remembering old times. This is what happens with old friends. And when we created RISE, and Satish and I were sitting down to figure out that we have to have a scientific advisory body to advise us. The question was, who should the other three be? Because there was one unanswered first person, and that was Didi. So we spent a lot of time figuring out who the other three should be. And perhaps there was unless my memory fails me, a long time ago, I connected you with BC.
And RISE was started
RISE.
then.
Yeah.
We had even proposed that time,
That's
the
right.
white
So that
paper
was
was there,
like-
but then it didn't take off.
No, earlier.
Before.
Even
Before,
even before,
2007.
only Devashish that it
Yeah,
was.
yeah.
Yeah.
So 2007,
So-
2008, 2009.
So we have come full circle. The people who were behind the idea that one was nurturing for a very long time and helped us think through. And it's great pleasure